To produce a reliable standard regression model, or a reliable regression model, a reasonable ratio of participants to predictors is required. Now, but what's reasonable? For a reliable regression model, Stevens says that you need 15 cases per predictor. While I defer to Tabachnik and Fidel, it should be, if I did defer to Tabachnik and Fidel, which is another core text in statistics, then it should be 50 participants, plus an extra 8 for each predictor if there are multiple correlations. So for testing individual predictors, it's more likely 104 participants plus however many predictors you have. These are rules of thumb and assume medium effect sizes. The first assumption is largely methodological and should occur in the planning stage of your research. The second assumption investigates normality. So each continuous variable should be approximately normally distributed. Now SPSS provides graphs in the form of box plots, stem and leaf plots, and normal Q and Q plots, in addition to statistical measures such as the skewness, kurtosis, normality tests of such as Shapiro-Wilk and Kolmogorov-Smirnov. Now they assess univariate normality. Multiple regression is also sensitive to outliers, and they should be dealt with to lessen the impact of the regression solution. Now there are two types of outliers. There are univariate outliers and there are multivariate outliers. Univariate outliers are those with extreme scores on a particular variable. They can be identified graphically with box plots and confirmed with z-scores. Multivariate outliers, on the other hand, are those cases that have unusual combinations of values across two or more predictor variables. They can be detected by something called the Mahalanobis distance. Now the fourth assumption looks at the assumption of multicollinearity and singularity. High correlations between predictors render multiple regression more unstable or very unstable and makes it really quite difficult to interpret. Singularity refers to perfect correlation among predictors, while multicollinearity refers to a very high correlation among predictors. Now correlations among predictors that are above 0.9 indicate multicollinearity, although it is advisable to avoid intercorrelations above 0.7, as regression does get difficult to interpret. The fifth assumption looks at normality, linearity and homoscedasticity of the residuals. Now remember that the residual is the difference between the actual and the predicted score of the criterion or the dependent variable. So these three assumptions are assessed graphically in this lecture. Okay, in this example we're doing a standard linear multiple regression. So let's take the easiest, well in this case we're taking the case of two predictors and we're trying to see how those two predictors form onto one dependent variable. So our dependent variable is exam score, and then we've got two predictors, hours and anxiety. Let's just see what they are. So if we go to variable view, we'll get a bit more of an idea. So we can see that hours, the variable name hours, is the hours, when you look at the label, is the hours spent revising for that particular exam. And anxiety, well, that's the anxiety, the felt anxiety, through some measure of anxiety that's taken, so some measure of anxiety, some test of anxiety, and that's their score on anxiety levels. So we can see that each of these scores are a scale, so we're going to now do a multiple regression on that. But to do that, we have to go through a couple of assumptions. But before I even do that, so what we can see here is a person who got an exam score of 55. Person who had an exam score of 55, they spent 26 hours revising for that exam, and they had a self-reported anxiety score on whatever anxiety test you're using there of 91. Participant 13, they spent 61 hours studying for their exam, revising for their exam. They had an anxiety level of 26 before they sat the exam, and in their final exam score was 72. So once again, we're trying to find out whether hours spent revising for the exam and anxiety level prior to the exam predicts the exam score, and we're using a multiple regression to do that. So the first thing we want to do is just check a couple of assumptions, and the first one is checking normality, checking to see if normality assumption is met across those three variables. So let's go to Analyze and Descriptive Statistics, Explore, and let's grab all three of those variables and put them into the dependent list there. And the statistics, we'll just leave it at descriptives there, leave the default. What about plots? Well, let's just plot by box plots. So again, all that does is just gives us an idea of a bit of an idea of what the data looks like in terms of normality and any potential outliers. And just to reduce the amount of information coming your way, we'll take out the stem and leaf, but in your own studies, I would use that as also a means to look at a graphical representation of your data. Let's tick normality plots with tests, which will formally test for normality on each of those three variables. And continue. We won't worry about the options. We'll leave that as a default, exclude cases listwise, and we won't worry about bootstrap. The case processing summary table shows just how many cases were analysed, if any were missed, if any is missing due to missing data or excluded due to missing data, and it gives us basically the number of valid cases in our data, and we can see that we have 20 valid cases in our data set. Now this table of descriptives contains lots of rich information from central tendency to range to skewness and kurtosis. Where I want to zero down on is skewness and kurtosis, and what I'm looking at are those skewness and kurtosis values, and I'd be dividing them by the standard error, which is in the last column, to have a look and just see if they're above, if that Z-score for skewness and kurtosis is above 1.96 or below negative 1.96, because if there are, then that's a warning signal for me that there's potential normality issues. And what I can see here is when I look at the Z-scores, so divide the values of skewness value by its standard error, or the kurtosis value by its standard error, I can see that there's no issues around normality that I can see looking at those figures. However, to do a more formalised test around normality, I would do the Shapiro-Wilk or the Kolmogorov-Smirnov test, and as I've mentioned before, if there's a disagreement amongst either of those tests, then I would choose to use the Shapiro-Wilk. And here this is testing normality. If I don't have a significant test, my normality assumption is met. If I do have a significant normality test here, then my normality assumption is violated. So here we can see the Shapiro-Wilk score for the three variables suggests that I have normality on each of those variables. So it's not violated. That assumption is not violated. Now you can also graphically look at your data using histograms, stem and leaf plots, box plots and so forth. And I provide a description here of the box plot, and the box plot's quite good just to graphically look at your data, see if there's any normality issues, any potential outliers. So if it looks quite symmetric, if the box plot looks quite symmetric around that median score, then you probably got okay, and you're okay in terms of normality. Also, you can see that when the box plot is done for each variable, you can see that there might be outliers or not. And outliers are indicated in a box plot, potential outliers, by a circle, either filled in or not filled in, and an extreme score by an asterisk. And we can see that that's not the case in this particular data set. Now, if there were any outliers on the distribution, then each would be denoted, as I said before, by a circle or an asterisk, and we'd need to adjust that. So if there were outliers, and there were no data entry problems, so you checked your data, then you've got a few options available to you. You could firstly delete. You could delete the cases that have outliers. And if you have a strong justification to do this, for example, they're not part of your population that you're interested in, then go ahead and delete. So for example, if I wanted to test somebody's hearing, a person's hearing of two different tones, and a particular person rocked up to the experiment and actually was deaf, and I didn't know they were deaf, and they got very, very poor scores on hearing these two tones, well, they would probably be an outlier in my particular study, but I'm not, they're not part of the population that I want to sample from. So that would be a reasonable justification to delete that particular outlier. Then another way to manage outliers, you might want to change the offending data points to 1 unit higher than the next non-outlier data point, or to 3 standard deviations above or below the mean of the distribution. And the third option available to you is to transform the variable, which would reduce the impact of the outlier.